Okay, we've started.
We're moving on to another section today. Again, it's still review phase. We're still going to be talking a lot about functions. This section shouldn't be too long. It's about combining functions. Combining functions. The notion is functions can be combined to obtain new functions. We can combine them using things that are called function operations. Nothing too fancy here. So something like one, we can add functions. And so we can say something like, so given functions like f of x and g of x, we can do things like f plus g of x, which is just defined as just adding f. Do this by adding like terms. We could put in a subtraction here as well. Adding or subtracting. Terms. Like terms are just terms that they look exactly the same except perhaps for the coefficients in front of them. So for example, find the sum of these two functions, adding them together by adding like terms. So we can do 2 plus 3x minus 7x cubed plus 7 minus 2x plus 4x to the fifth. And what you do is you combine the like terms. So you can have constants that you're going to add together, the 2 and the 7. These are guys that do not have any variables on them. They're just numbers on the number line. Those are considered like terms because they look the same except for the coefficients. Plus, you can add the x terms. So here are two numbers. These are considered like terms because they are both multiples of x. The only difference is their coefficients, so those are considered like terms. That's 3 minus 2. Plus, there's no other term, so there's the x cubed term. You just leave that by itself, so that's a minus 7x cubed. Plus, there's no other x to the fifth term, so you leave that by itself. That's there too. So at the end of the day, now you just combine these like terms. You take the 2 plus the 7, you get 9, plus you take the 3x minus the 2x, you just get x, minus 7x cubed plus 4x to the fifth. And so that's the answer. In general, the order you write these things in won't matter. So I don't particularly care if you write in ascending order, descending order, or jumbled. It doesn't matter. Everyone okay with that? That's not strange. Just want to make sure everyone's on the same page. So you can add and subtract functions. We can also divide functions. So you can think of this in the function realm. This is just creating a new function where the rule is add these two other functions. So it takes the input as these functions and the output is the sum of the functions. We can, of course, multiply functions. That is given f of x and g of x. We can find fg of x. And this is equal to f of x times g of x. We do this using the distributive law, right? So basically that means you take each term in one of the functions and you multiply each other term in the other function, and then you add all the answers together. So, for example, I can take f of x equals x plus 2, take g of x equals 2x squared minus 3x plus 1. So I can define fg as putting both of these functions in parentheses equals 2. And how you compute something like that is you take each individual in one of these. It doesn't matter which one you start with, but I'm just going to start with this one. The term x, I'm going to multiply that, multiply that, multiply that, and I'm going to add those all together. Right? So I'm using the previous function in that regard. So, and we know from laws of exponents that when I multiply things of the same base, we add the powers. This is an x to the 1 power, that's an x to the 2 power, so I can multiply these, and the power becomes 2 plus 3. So that becomes 2x cubed. Does everyone get that? Nothing strange there. X times this, the powers are both 1, so the powers add to become 2, and so I would have minus 3x squared. X times 1 is just x, plus, and now I do the same thing with the 2. Boom, boom, boom. So 2 times this is 4x squared, 2 times this is minus 6x, 2 times 1 is just 2. And now we combine like terms. So one term at a time, look at x cubed. That's the only x cubed, so you just write that down. Now x squares, I have minus 3x squared plus 4x squared. That becomes 1x squared. In terms of x, I have 1x minus 6x. That becomes minus 5x. And in terms of the constants, I just have a 2. So that would be the answer. Questions? I don't think I would be saying anything strange, but if I am, you need to stop me and tell me. As well as it's good to remind you, because a lot of the times, it's not that something is difficult, it's just that we're going to be doing problems where you're going to have to be doing multiple things at the same time, so you're going to be having to do something where you have to add the functions while doing something else. So it's good to just refresh your mind about how to do the basic fundamental things, and then you're going to sort of cook them up into more complicated sequences. 3. We can divide functions. So we can create f over g of x equal to f of x divided by g of x. And this works, of course, when g of x is not equal to 0. So this function will be undefined whenever your denominator is 0. Some things to note here. There are times when you might need to simplify something like this. Note that you can expand across the numerator. Right, so that's something like, okay, I'm taking something like a plus b and I'm dividing by c. I can actually expand that, split it up, and do that. That is perfectly fine. So for example, if I have take that, and I can simplify that by doing x squared divided by 4x, 7x divided by 4x, plus 1 over 4x. I can further simplify that by canceling, because there's multiplication, so this is x over 4, plus the x's can cancel, this is 7 over 4, plus this I can write as something like 1 over 4, x to the minus 1. A common mistake, by the way, is to think that this comes up and a student will write a 4 in the top. That would, of course, be incorrect. When you see something like 1 over 4x, it's actually the entire thing raised to the minus 1, which the laws of exponents would say that happens. So it's still a quarter. So even if you bring the x up, its coefficient needs to stay down. Okay, that happens every so often. It's also important for you to remember another common mistake. You cannot expand across the denominator. So, for example, what do I mean? If you have something like a and there's a sum in the bottom, you cannot do this or anything similar to that, right? If there's a sum in the denominator, you can't split the fractions across the denominator the same you can do it with the numerator. Okay, that is actually completely incorrect. Okay, so that's something you should know. So, for example, if you have x over x plus 2, this is not the same as you saying x over x plus x over 2, which is 1 plus x over 2. It is actually incorrect to say that. Okay? You have x over x plus 2, it's x over x plus 2. There are other things we can do with that. There are cases where we'll want to simplify something like that, but you would not simplify it this way. You would simplify it doing something like polynomial long division or synthetic division. We'll probably need to simplify something like that towards the end of the course, not really so much here. And I'll remind you, I've been polynomial long division when we get to that. We might not get to that situation. So those are just some things, right? So when you're dividing functions, the denominator cannot be 0. You should not expand along the denominator, but it's okay to expand along the numerator. There will be situations where that will be important. What else? You can compose functions. Composite functions. These are going to be super important. As the form f of g of x, right? So we've seen this before in the quiz and so forth. But basically it means you can take one function's output and plug it into another function, right? An alternative notation, you might see that. This was on the bonus for the last quiz. F with a circle and a G means exactly the same. Take the right function, plug it into the left function. And as we've seen here, what this means is replace each instance of x in f with the function g. So it doesn't mean multiplying them. So if you see this and I put parentheses here, it's not multiplying. In fact, that's something you should pay attention to. So if I put the parentheses around the two functions, that's multiplication. If I put the parentheses around the g of x, that's composition. These are two very different operations. So these are not the same. Right? This is saying I'm multiplying the two functions, so I'm applying the distributive law. This is saying I'm actually plugging one function into the other function. Say you have to do those things. So we can say that's equal to f of g of x. Which basically means in f of x, all the x's are going to be replaced by g. So this means I'm going to essentially recopy this function, except instead of x, I'm going to open a parenthesis. And I'm literally going to write g inside that parenthesis. So I can write g. So this will give me, my g is actually that guy, x squared minus 2x plus 1 plus 5. And we can actually combine it. X squared minus 2x plus 1 and the plus 5 can be combined to get plus 6. Someone tell me how to do this one. Yeah?
So you're going to do like radical f of x plus 5. So then it's going to be radical, then in parentheses, x plus 5. Yeah, radical x plus 5.
So we have the radical of radical x plus 5 plus 5. Can we simplify that further? Yeah?
You could do the first s plus 5 to 1/4, and the second one is just plus root 5.
So 1/4?
Yeah.
And then do what?
Plus root 5.
Plus 5?
Root 5. Square root 5. Yeah.
Is that correct? You're shaking your head. What's wrong? Okay, what did we say radicals were? But really, power is in disguise, right? So this you could have thought of as this. So what is this tantamount to? You actually put the half power on that to get a fourth, and then the half power on that to get that, which is distributing powers across sums. That's actually illegal. This is what I mean. When I'm teaching you something else and you have to remember some basic rule from before, it starts to get confusing. That's why I'm going over everything. Okay? So yeah, you would leave it as this, right? Doing that is a no-no. That is what's called distributing a power across a sum. Okay, so you need to be careful, right? So I know I'm going over some basic things, and some of you might be rolling your eyes. Why do I have to look at this again? It's important, right? We're going to be doing a lot of things all at once, and you slip up on one of these basic rules, and it's all over. Yeah.
So in its simplest form, it's that.
That's the simplest one. So
Okay.
if I gave you this question on a quiz, you need to stop here. If you went here, it's all over.
Okay, because of that rule.
Because of the rule. So you were absent on the first day of class.
Yeah.
So I spoke about several things that you should never do. Distributing powers across sums was one of them. So if you have a plus or a minus separating terms and a power, you can't put that power in each individual thing.
Okay.
It's actually illegal.
Okay.
Right, but it's very, trust me, it's a very common mistake. A lot of times when you're doing something else, your brain forgets that, oh, there's this other thing that I need to be paying attention to. It'll take some juggling, but it's something that you're going to have to get used to. So you cannot do that. Let's go to G. What do you do here? Yeah?
It'd be g of x squared.
What is G of G?
Yeah, g.
I leave that here.
Minus 2g of x.
So essentially the habit, especially if you're kind of sketchy on algebra and it's been a while, or I would really recommend that you actually take the step to do the exercise where you just recopy this, but you just write gaps where the x's were supposed to be, just to be safe for the time being. And I even suggest, in general this line is not necessary, but I even suggest that you first write g of x in that gap. So you know that I'm going to put this entire thing in side parentheses. Okay, just to remind yourself about it. So here, we literally put that entire thing here. Square minus. Now, at this point, you need to resist the urge of taking that 2 and just writing this as x to the 4th, 2x squared, and 1, right? Because you can't do that. If you wanted to expand this, you could. You'd have to use foiling, where you have those 2 parentheses, and you take each of the 3 terms here and multiply each of the 3 terms there. I won't really do it, but that's how you proceed. But for now, we can stop here. So just, you should note that this is actually this. So multitasking is actually quite difficult for your brain to do, so don't underestimate the things I'm telling you here. The idea being, there was a famous computer scientist and mathematician, John von Neumann, And one of the things he's quoted as saying is, you know what, you never get good at math, you kind of just get used to it. You know? So there will come a point, if you practice enough and if you expose yourself to it enough, it'll kind of be like grammar. When you actually make a mathematical mistake, it'll feel weird to you, like kind of using bad grammar, because a lot of times grammar is, the rules is so arbitrary, but you know how to speak correctly because you've heard it so often. You know about subject-verb agreement. You feel a gut feeling. That's kind of where you want to aim. Where if you actually distribute a power across a sum, it feels weird. That's where you want to be. You know? Because then it takes the multitasking thing process out. Your brain just kind of does it without thinking about it. Okay, but in the meantime, to get there, you really kind of want to be careful and really write down each step. Even though you might not think it's necessary, it's going to be important in the long run. Eventually you'll get faster and faster and faster, and then eventually you'll be able to leave this out and write that and so on and so forth. But it takes some time. And especially if you're slightly uncomfortable with math, which a lot of people are, for various reasons, you really want to take the time and do things properly. It's kind of why I'm going over these basic things, even though technically none of this is calculus. It's all still algebra. When we're doing calculus, we're going to be doing these things while doing calculus, and I want you to be very careful. Okay. How about this?
It's like the one we had before, except the x you had left, you just plug in another radical.
Okay, so it's f of f.
Yeah.
Okay, so tell me how to proceed.
Well, so radical. I don't know how to explain this. So another radical. I'm just gonna because it's like radical, and then you put another radical, x plus 5 plus 5. Right. No, we're missing a radical.
Where?
Like
here, in front. This one.
like where the x is, that's supposed to be. There's supposed to be like 3 radicals.
Oh, okay. So this one should be another radical.
Yeah, and then in there, x plus 5, and then plus 5. Yeah.
It's like confusing. So I think that would be the answer, but let's actually just make sure. So again, let's go back to basics. What did we know? When I look at this, what I'm going to think of is I'm having an f, and I have this replacing all the x's. So I'm really going to write this guy, open a gap for the x, and inside that, I'm going to write f of x. Then I keep doing this process, right? So here I have f of f, which means I'm going to start copying the function f, but I'm going to leave a gap, and inside that gap, I'm going to write f of x. And then again, here's that gap, I'm just going to write that in. So it's that radical, x plus 5, plus 5, plus 5, and that's it. So that is the last thing I want to remind you that shows up in this section, I'm not going to do any detailed examples or anything, but just to remind you, is what's called transformation of functions. So this is your given function f of x, and c is a constant. Let's make it a positive constant just to make the rules nicer. So these are certain composite functions and function operations that you can do on a single function, and they actually have effects on something like the graph of the functions. So for example, if you're given a function fc is a constant, what would f of x plus c do to the graph?
It would go left.
It's a shift left c units, right? So that's, for example, if you start with y equals x squared, and you want to know what does y equals x plus 2 squared looks like, well, that's just a shift of this guy left by 2 units, and it would look like that. So you can get to things. F of x minus c is a shift right c units. You'll notice a pattern here that when you're messing with the x, things kind of have the opposite effect of what you think they'd have. So adding actually moves left and subtracting actually moves right. Dividing actually stretches while multiplying actually shrinks. It's kind of reverse. So if you're doing something like f of cx, this is a stretch if c is bigger than 1, and a shrink if c is so for example, if you have a function that goes up to 1 and does this, and that's your f, then your f of, say, 5x, that's actually going to shrink it to 1/5 of its size. It'll actually shrink it. While if you have f of x divided by 5, that actually stretches it to 5 times its size. The idea is you're giving the output a smaller number to work with, so it has to overcompensate by making the y value bigger. If we have something like the constant is outside the function, and this stretches when you kind of think it will stretch. Sorry, I should be doing a horizontal swing. Then I can do this. So let's say this went up to 1. So now that will happen in 1/5 of the time basis. Because I'm changing the x affects the horizontal. That's going to stretch it out. This is the one. This stretches horizontally. If c is greater than 1, it shrinks. I think I was thinking of horizontal. So it's stretch if it's less, shrink it. Stretch is bigger, shrinks it. Vertical. So if your f of x is this guy, and if I take 5 times f of x, it stretches it vertically. So this would go to level 5. Before it was level 1. If I take f of x times 1/5, it shrinks it vertically. So we'll go to 1/5 its size. If you make the x negative, what does that do to a function?
Shifts down. No, it flips it.
Flips it where?
To the vertical. Or over the x-axis.
It flips, or the technical term is reflects, in which axis?
y-axis?
It's the y-axis. So, for example, you can have a function here that I can call f of x. Then my f of minus x is actually going to be this. Flip in the y-axis. If you have the negative on the outside, this reflects in x-axis. Right, so if my f is something like x squared, then minus x squared is going to actually be flipping upside down. So this is f of, minus f of x. And this is f of x. We can do multiple transformations at once. In doing so, follow PEMDAS. You guys remember what PEMDAS is? Parentheses, exponential, multiplication, division, addition, and subtraction. This gives you the order of operations, the order in which you should do something. So if you see a function like you multiplied it on the outside, you shifted it here, and then you added another thing. If there are any parentheses, you do what the parentheses tell you first, but in this case, you would first take the graph and you would shift it to the left, then you would stretch it vertically, then you'd shift the entire thing up. Which I don't think I told you about that when you do that. So the order in which you do these shifts with your graph will matter. This is shifts graph up. So you have something like y equals x squared. This is your f of x. And if I say f of x plus c, or x squared plus 1 or something like that, it's going to be your f of x plus a constant. This guy shifts down. So just put something like f of x equals x squared. And if you have something like f of x minus 4, which is x squared minus 4, this is shifting the x down. We'll stop there. That's section 1.2 completed, so the homework for that is due on Tuesday. And then we'll start doing some more fun things. Did you guys do exponential functions in pre-calc? So a little bit more review, but not for long. And we'll get into calculus by, if not late next week, early the following week, we'll actually start doing some calculus.